First, what is a linear function? A linear function is normally shown as f of x equals to mx plus b, where for every input of x, there is an output of y. It's like a factory. You input any value of x, and it will give you a value of y. In this equation, m is the slope or gradient, and b is the y-intercept of the line. We can find the gradient of a line using the equation y2 minus y1 over x2 minus x1, where y2 and x2 is a point on the graph, and y1 and x1 is so too. In this example, there are points 3, 4, and 1, 2 on a line, thus giving us the gradient of 1. How can we determine if something on a graph is a function? Well, this is where the vertical line test comes in, where we draw a line on the graph to determine if something is a function or not. Take this parabola for example. It passes as each value of x only has one corresponding y value. On the other hand, the circle fails the vertical line test, as there are multiple corresponding y values for one value of x, which is not what we want for a function. There are a multitude of forms of linear functions, and today we'll discuss a few of them. First is the slope-intercept form. Y equals to mx plus b. This form makes it easy to read out the slope m and the y-intercept b. Here are examples: y equals to negative x plus 5, clearly showing a slope of negative 1 and a y-intercept of 5. Next we have the point slope form. Y minus y1 equals to m times x minus x1. This form is useful if you know a specific point on the line, x1, y1, and the slope m. For a line, using the point 0, 5 and the slope negative 1, we get y minus 5 equals to negative 1 times x minus 0. This emphasizes how the line can be constructed from a single point and its slope. Another perspective is the intercept form. X divided by a plus y divided by b equals to 1. In this form, a and b are the x and y intercepts respectively. Since the line crosses the axis at 5, the equation can be written as x divided by 5 plus y divided by 5 equals to 1. Finally, we have the general form, ax plus by plus c equals to 0. This form is quite overarching and can represent any linear equation. Here we have x plus y minus 5 equals to 0. Though not as visually intuitive as the slope-intercept or point-slope forms, it's another standardized way to represent the line. Unlike the slope-intercept form, which immediately shows the slope and intercept, the general form emphasizes a more algebraic perspective. Its key advantage is its versatility. It can represent vertical lines and all other lines without issue. It makes certain algebraic manipulations, like solving systems of equations, more straightforward. And it directly gives a normal vector, AB, to the line, which can be useful in geometric calculations. In short, while less visually intuitive, the general form is a powerful, standardized tool for working with linear equations. Now, let's continue by identifying the different descriptions for linear functions. Let's start by understanding this function in words. A function that has two key characteristics. First, it has a slope of 2, meaning that for every 1 unit we move right, the function rises by 2 units. Second, it has a y-intercept of 1, which means the function crosses the y-axis at the point 0, 1. Algebraically, if we write this as f of x equals to 2x plus 1, where 2 is our slope and 1 is our y-intercept. Now, let's visualize this function on a coordinate plane. Notice how the line passes through 0, 1, confirming our y-intercept. As we move right 1 unit, the line rises 2 units, showing our slope of 2. This can also be found using the formula for the gradient y2 minus y1 over x2 minus x1. The red line extends infinitely in both directions, representing all possible input values. The straight line here also indicates a constant rate of change for the function. Now, in a tabular representation, we organize specific input-output pairs of the function. Here's a table of several x values, ranging from negative 2 to 2, and their corresponding f of x values. As you can see, when x equals to negative 2, f of x equals to negative 3. When x equals to 0, f of x equals to 1. And when x equals to 2, f of x equals to 5. This table gives us specific values for x and f of x, showing how the function works at particular points. It's a very useful form where we need exact values for certain inputs. This also enhances our understanding of what a function is. As you can see, an x value is plugged into the function machine and is run through 2x plus 1 to give us the output of y. These types of representations are helpful when we need to evaluate the function at specific points or when we're trying to find patterns in the data. It can also be useful when finding a gradient, as all the points are clearly laid out. Finally, how do these four different representations of the same function compare to each other? Well, all representations describe the same linear function, f of x equals to 2x plus 1. The algebraic form provides a precise mathematical expression, while the graphical form shows the continuous relationship between x and f of x. The tabular form gives specific input and output pairs, while the verbal description explains the function's detailed behaviors. For example, let's say there is a car rental company that charges $40 a day plus a one-time fee of $25. How much would it cost to rent for a different number of days? Now, the equation here is f of x equals to 40x plus 25, as the y-intercept is essentially what you first start with, and 40 is for each subsequent day. For example, say you rent a car for 7 days. This would mean that you would need to pay a price of $305, as it is 40 times 7 plus 25. How this works is that x value goes into the function machine, it processes it through the equation, and we get the y value of 305, or the total cost. So, how can we determine if something on a table is a linear relationship or not? Well, we can look at the common difference, or CD. In here, we see that there are days to cost on the table. For one day, the cost is $65. For the second day, the cost is $105. For the third day, it's $145. This is a linear relationship, as there is a clear common difference of $40 being added for each subsequent day. Meanwhile, the table on the right is a nonlinear relationship, as there is no clear common difference, jumping from 2 to 8 to 18 without any linear pattern. Here's another problem to consider. A company manufactures widgets. The cost to produce X widgets is represented by the function of C of X equals to 50 plus 20X. The revenue from selling X widgets is R of X equals to 30X. Our goal is to determine the number of widgets the company should produce to maximize profit. Let's explore the first method, the algebraic approach. First, we define profit, P of X, as revenue minus cost. Substituting the given functions, profit equals 30x minus the sum of 50 and 20x. Next, we can take the derivative of the profit function with respect to x. The derivative is constant 10. Setting the derivative equal to 0 to find critical points gives us 10 equals to 0. This result indicates that there are no critical points. Therefore, profit increases indefinitely as production increases. The justification here is straightforward. Since the derivative of profit is a constant and positive, profit continues to rise as production scales up. Now let's visualize this with the graphical approach. Here we've plotted the profit function P of x equals 10x minus 50. The straight line has a positive slope, indicating that as the number of widgets it produces increases, so does the profit. The graph further confirms our algebraic findings. A straight line with a positive slope means that profit grows without bound as production ramps up. Finally, let's examine the tabular approach. We've constructed a table showing different production levels and their corresponding profits. Starting from 10 widgets, each increase of 10 widgets results in an additional 150 in profit. Observe how profit consistently increases as production increases. This step-by-step increase aligns with our previous algebraic and graphical analysis. The table reinforces our conclusions. As the number of widgets produced rises, so does the profit, confirming that higher production leads to higher profits. In conclusion, all three methods, the algebraic, graphical, and tabular approaches, demonstrate that the profit increases as the production increases. Therefore, to maximize profit, the company should produce as many widgets as possible. Now we know how a linear function can establish correlations and relationship between two different things such as time and cost. However, what if we need to find the area under a curve? This is where calculus comes into play. Imagine a car is moving along a straight road. Its velocity is meters per second, depends on time, t, and is given by the function v of t equals to 2t plus 3. Suppose we want to find how far the car travels between t equals to 0 seconds and t equals to 5 seconds. To understand this, let's graph the velocity function. On the horizontal axis, we have time in seconds, and on the vertical axis, we have velocity meters per second. The line v of t equals to 2t plus 3 starts at 3 meters per second when t equals to 0 and increases steadily as time passes. Here's a crucial insight from calculus. The distance traveled is the area under the velocity time graph. If you think about it, velocity tells us how fast something is moving. If you multiply velocity by a small increment of time, you get a small piece of distance. Summing all these pieces of distance over the entire time period gives the total distance traveled. Graphically, this is exactly the area under the velocity curve from t equals to 0 and t equals to 5. Before we directly jump into integration, let's approximate the area using Riemann sums. We'll divide the time interval from 0 to 5 seconds into smaller segments. For each segment, we take the velocity at the left endpoint to determine the height of a rectangle. By adding the areas of these rectangles, we get an approximation of the total area under the curve. Each rectangle's height represents the car's velocity at that moment, and its width represents a small time interval. While this is only an approximation, it helps us understand what we're trying to achieve with integration. As we make the time segment smaller and smaller, our Riemann sum approximation becomes more accurate. In the limit, this leads us to the concept of the integral. The definite integral from t equals to 0 to t equals to 5 of v of t gives us the exact area under the curve, and therefore the exact distance traveled. Mathematically, we write distance equals the integral from 0 to 5 of v of t dt, which equals to the integral of 0 to 5 of 2t plus 3 dt. To solve this integral, we find the antiderivative of 2t plus 3. The antiderivative of 2t is t squared, and the antiderivative of 3 is 3t. Combining these, we have the integral of 3 dt equals to 3t. Thus, the distance equals to t squared plus 3t evaluated from 0 to 5, which equals to 5 squared plus 3 times 5 minus 0 squared divided by 3 times 0, which equals to 25 plus 15 minus 0, which equals to 40 meters. In conclusion, we started with a velocity function and used a relationship between velocity and the area under the curve to find the distance traveled. By integrating the velocity function over the given time interval, we found that the car travels a total of 40 meters between t equals 0 and t equals to 5 seconds. This illustrates a key idea in calculus. Integration connects rate of change, like velocity, back to the cumulative quantity, like distance. Another important concept are inequalities and literal equations. Here we have a basic inequality of x is larger than 2. This can be represented on the number line through an open dot at 2, an array going from 2 onwards to where x is larger than 2. This can be also represented graphically, but the area on the right of the graph are all values of x as it is greater than 2, or the vertical line of x equals to 2. Next, let us explore compound inequalities, starting with an AND inequality. Negative 2 is smaller or equal to x is smaller or equal to 3. This inequality means x is between negative 2 and 3, including both endpoints. This can be represented on the number line with the points negative 2 and 3 marked with yellow dots, with a green line highlighting the valid values for x, which are between negative 2 and 3 on the line. When we visualize this graphically, we draw vertical lines at x equals to negative 2 and x equals to 3, marking the boundaries of the solution. The shaded region between these lines represent all the valid solutions to the inequality. Now let's look at a compound OR inequality. X is smaller than or equal to negative 2, or x is larger than or equal to 3. In this case, x can be less than or equal to negative 2, or greater than or equal to 3. We can see two separate regions on the number line. The first region includes all values less than or equal to negative 2, and the second region includes all values greater than or equal to 3. On the Cartesian plane, we draw vertical lines at x equals to negative 2 and x equals to 3, marking the two distinct regions where the solutions to the inequality lie. The shaded areas to the left of -2 and to the right of 3 represent all the valid solutions for x. Finally, we turn our attention to literal equations. A literal equation is an equation involving variables where one or more variables are solved in terms of others. For example, in the equation a equals to pi r squared, we can solve for r in terms of a and pi. This can be done through adding, subtracting, multiplying, dividing, or any other mathematical process to both sides of the equation to simplify it while making everything balanced and equal. Here are some key points for inequalities and literal equations. Inequalities show a continuous range, or inequalities show separate regions. Literal equations can be solved for any variable, and a filled-in dot is inclusive, while an open dot is exclusive while representing an inequality on a number line. After watching this video, I hope that you derive some knowledge from the essence of linear functions and calculus to help you in your future mathematical calculations. Thank you for spending 16 minutes of your day with us to help enhance your mathematical knowledge. I hope this was helpful and impactful to your life. Thanks for watching.